Ever wasted hours on a cloning reaction that didn't work? Picked the wrong method and ended up with nothing? Let's fix that. Today we're solving the classic dilemma: Golden Gate or Gibson Assembly? Because choosing wrong isn't just annoying, it's expensive. Let's apply this to a real lab situation. Say you're assembling a multi-gene construct. You're staring at your fragments, wondering which one you should use. Golden Gate or Gibson? In this video, I will break down the two methods, then move to their strengths and limitations, to finish with how to choose the best method. Let's start with saying that both methods are powerful, both single-pot, scarless are seamless, and fast. But they use different enzymes and serve different purposes. Here's how each method works. Golden Gate uses type 2S restriction enzymes, which cut outside their recognition sites, generating specific overhangs of 1 to 5 nucleotides, for seamless ligation and no residual cloning scars in the final construct. Gibson Assembly relies on large overlapping ends of 20 to 40 base pairs created by an exonuclease. This enzyme chews back the 5' ends, generating single-stranded overhangs that can anneal to adjacent DNA fragments. DNA polymerase then fills in the gaps, and DNA ligase seals the molecule. Golden Gate is brilliant, but not foolproof. The good first, standardized parts or overhangs allow for modular cloning, combining fragments in a predetermined order. High complexity makes it ideal for building complex gene circuits. It's highly efficient because the final product cannot be cut by the same restriction enzyme, increasing the yield of desired colonies. The method is well suited for high-throughput cloning, especially for constructing gene circuits and complex biological systems. Unfortunately, requires careful upfront design of DNA fragments and primers to ensure correct overhangs. It needs dedicated destination vectors designed for the method, limiting its use with standard plasmids. To prevent interference with the assembly, the required type 2S restriction sites must be removed from the fragments and destination vector, a process called domestication. The initial planning, primer design, and setup can be complex and time-consuming. Finally, due to the small size of the overhang, large fragments are not efficiently assembled. Gibson Assembly is flexible and forgiving, but it has quirks. Unlike Golden Gate, you do not care for unwanted restriction site. It can join DNA from various sources, including genomic DNA and PCR products, without the need for domestication. The assembly takes 15 minutes, and the large overhangs are ideal for assembling large DNA fragments. However, while some commercial kits offer high fidelity, homemade Gibson Assembly can introduce errors at fragment junctions. Fragment less than 200 base pairs are more susceptible to being degraded by the exonuclease. GC-rich or stable secondary structures at the fragment ends can interfere with the assembly. And although generally robust, efficiency can vary, particularly when assembling more than 6 fragments. So whether you're optimizing for speed, modularity, or sequence flexibility, this flowchart can guide your choice every time. If you have more than 6 fragments, go Golden Gate. If your fragments contains type 2S sites, go Gibson. If some of your fragments are smaller than 200 base pairs, Golden Gate is best. If some of your fragments are bigger than 4 kilobases, go Gibson. If you are cloning in a Golden Gate specialized vector, it's Golden Gate, but you can also use Gibson. To sum up, Golden Gate thrives on modularity and speed. Gibson wins on flexibility and precision. In the end, they are both champions of DNA assembly. I hope you enjoyed the video, and that it helped you dodge a cloning disaster. If it did, go ahead and hit the like button. It really helps the channel and it keeps the science flowing. Subscribe for more lab survival guide episodes, because science shouldn't suck.